Welcome one more day to the TecnoDigital School. In today's video, I'll be looking at how to export data from free body cuts into Python, into our scripts. And we will do this through this example that we see here. We'll see how to export and extract all that data, the profile of axial forces, shear forces, and bending moments as well. So let's get started. In one of our previous videos, we explained how to extract free body forces from our models. We saw that we had to ask for the N4 variable in case we have solid elements, or the SF variable when we have shell or beam elements, as it is this case. This is the example that we saw in that video. Let's summarize very quickly how can we visualize these results. If we come down here to View CAD Manager, and we enable, for instance, the Y plane, here, we are cutting our model. However, we cannot see it very well. So we can come up here to ODB display options, enable render beam profiles. OK. And there we have our beam. Let's display results here. And let's add some shading as well. So we come up here to common options, shaded, OK. And there it is, much better. So we have made our cut here. We can move this cut with this slider down here. And to visualize the free body forces, we only have to click here, this last check. And here we can see the forces that we get. These are resultant forces. This is the total force that we have, and this is the total bending moment that we have. But the question now is, how do we extract these values, these forces or bending moments, into data that we can manipulate in our Python scripts? The key to achieve that is to use this function, xy data from free body. And we can call it from the session. We say session.xy data from free body. We specify the ODB from which we're extracting data. And then all the arguments that we will see are very easy to understand. If we want to extract force, yes or no, true or false, we can specify the bending moment, even heat flow rate. And for all of these variables, we can specify if we only want the resultant or if we want the component number 1, 2, or 3. All of these are Boolean variables. So back in Abaqus, I'll go down here to the command line interface. If we run this full command down here, we want force, moment. We don't want the resultant, but we want each component. And we run this. We get an error because the variable ODB is not defined. We have to put something into ODB. So let's say ODB equal session.odbs, because I already have one ODB opened. Open a square bracket and tab to autocomplete. Like this, we already have the ODB that we have up here, frame.odb. So we hit enter and let's run it again. And what we get are 6 XY data objects. These objects contain all these values that we have extracted from the free body cut. For instance, the force component number 1. So this should be the X component in the X axis. I will show another viewport like this and then plot it. Yeah, here it is. We have the X component, the Y component, which is negligible, 10 to the minus 9. Or the Z component, which is also very, very small. If we plot all the force components, we only have component number 1. And the same for the bending moments. We plot them, we can see that we have some value around 250,000 newtons per millimeter in the moment component number 3. And these are the free body forces that we have right now. If we change the position of this cutting plane, come here again, and we move this downwards, we have different values, for instance, for the bending moment. And now if we run this again, this command again, and we extract the forces again, now what we will have, if we compare these two bending moments plot, then we can see that we get different values because we are in a different position. In this case, the cutting plane, the free body forces that we get are different. This functionality enables huge opportunities so that we can, for instance, create free body force diagrams of our models. In case we have beams or in case we have solids or shells, we can do that. And this is what we're going to do in the next example. To generate this example, we will use a Python script that you can download from the blog post. I will come here to run this script, file, run script, script tube, okay. And here it is. Here we have our model. We can take a look at the mesh, and the geometry that we have here, it's a curved hollow tube made of steel using solid elements. We are using incompatible mode elements, so we don't have problems with bending. And we are fixing the base down here, this region down here. Let's go to the loads. We go, boundary conditions. So here we have this face down here fixed. All the translations are fixed. And we're applying some load in the X direction on this face. We can see it here. So let's run the model. Submit the job. To obtain free body cuts in the field output, we have asked for the nFork variable. Here it is, nFork, because these are solid elements. So once the simulation is completed, right-click, results. One quick tip here, if you want to start recording a macro so that everything what we do now will be recorded and you can take those Python commands and use them, because we will be using those later. So we have our simulation completed. This is the deformation that we have. It is stretched in the X direction, mostly because of bending. And let's visualize these free body cut forces again. So we come down here. Let's open the ViewCut Manager. I will select the X plane. And again, we can move this plane and select different cutting positions. We have to enable free body cuts. And once more, we have the resultant force and bending moment. However, to extract more meaningful results in this model, we can use a different option to move this cutting plane, because now it's normal to the x-axis, as we can see here. What if we could rotate this plane? Well, we can do that coming here to rotate, and we should rotate around the z-axis, axis number 3. So if we choose this axis number 3 and we move it, now we are rotating the x-plane, the plane normal to the x-axis, around the z-axis. So it's actually rotating around the center of this circumference of the curve of the tube. So we can see, and we could extract the bending moment and the resultant forces that we get. And if we do this incrementally from 0 to 90 degrees, we will be able to plot, to visualize the free body diagrams of the structure of this tube in this case. The Python command that we want to use, the most important one, is this XY data from free body. And this is all what we need. One of the most important things is the ODB. We have to take the ODB. There are some ways to do this. We can introduce it by hand, but if we want to look at the current ODB that we see on the screen, we can get the ODB from the viewport that we are selecting at that moment. So to take the viewport, we can write session.viewports, and in here we would write viewport 1, viewport 2, my viewport, whatever the name. This is a string, but we can take the current viewport like this, current viewport name. So in my view, we have the viewport. And now from the viewport, we can obtain the ODB like this. From my view, ODB display name. This is also a string with the name of the current ODB. So finally, we have the variable ODB and we can plug it here. Very well, with this script, we can run this function and obtain some results. But what if we want to iterate? We want to move the plane or rotate the plane. Well, in that case, we could use a loop and change this rotation angle in each iteration. So let's create first an array with the different angles that we want to evaluate. So we could say angles equals np.linspace from 1 to 89 degrees, and ncuts is a variable which contains the number of points, the number of angles that we will have, evenly spaced between 1 and 89. So let's say this number of cuts is 10. So we'll have 10 points on which we compute these free body forces. And now we iterate for angle in angles colon, and that's it. The only thing that we're missing is to change, to rotate, in this case, the plane. Let's do that with the following function. We take the cutting plane that we have to activate it before, that's important, and then we change the value, in this case, the value for the angle. And like this, we will rotate the angle and extract the free body forces on each of these iterations. The next thing that we want to do is to read that data, that XY data objects, these straight lines that we saw before. And for that, we can put all these XY data from free body into a variable that we will call data list. And now we're going to read the first of these XY data objects. So to extract this, we have to write data list. We only want the first one, so that's the fx, the first component of the force. And to read the data from an XY data object, we have to write .data. And here there are some tricks that we can use. And the first one is to say zip star, because data is going to give us a list of points with the time and the value of the force, in this case, like XY values. And with this, instead of a list of points, we'll have two lists. One with the time, the X coordinate, and another one with the force, in this case, which would be the value, the Y coordinate of these points. This will give us two lists, T and F. But if we only choose one, it will give us F. But this will give us the force along all the frames of the analysis. So what we can do is to only read the last one. So we could say -1. And this is going to give us the value of the force in the X direction, let's call it Fx, in the last frame. This is very important because data gives us lots of data, lots of points, and we only want to get one value, one scalar. And once we have this, we are reading the force in the X direction in each iteration. What we can do is to store this force. Let's say force X, let's create a list, and let's add this value to this list, force X, dot append, Fx, and that's it. Like this, at the end of the loop, the force X list will contain all of the values of the X component force along all the cuts. To visualize this list of values more easily, we can run the following command. And this is equivalent to introducing into Abaqus these values, the angles, so from 1 to 89, and each of the values of the force for each of these angles. To make it more clear, we are doing like coming here to create XY data, keyboard, continue, and we're introducing here the value for the angle, for instance 1, and the value for the force, let's say 30. One more thing that we can do here is to specify the exact magnitude that we have. So the magnitude in the x-axis is angle, and the magnitude in the y-axis, in this case, is force. Here it is. So this is what we are doing here as well. We are specifying the magnitude type for the x-axis and for the y-axis as well. So let's save this script and let's test it. So in Abaqus, we go to File, Run Script, Script Free Body Forces, OK. And there it goes. We've seen how the X-plane rotated, and we have extracted all these results. Well, we have here this force X, which is our own XY data object that we have generated at the end. The rest, all of these force components, 1, 2, 3, etc., are from each of the cuts that we have made. So let's plot this force X. I will open another viewport, put it here on the right, and plot force X. Nice, we have now all the force in the X direction that we have extracted. So for each of these points, we can visualize them here, X, Y curve options, and we select show symbol. Okay, like that, better. Each of these points has been extracted from a different cut, and we have put them all together. So from angle 0, we have this value, around 4,000 newtons, and for the angle 90, it goes down to 0. So there is something that really doesn't make a lot of sense here, because actually the force, the only force that we are applying, if we come here to our model, I will zoom in a bit more, we can see that the force in the X direction is around 4,000 newtons. So, well, actually, if we rotate this back to the origin, more or less, this value is always 4,000, because actually the only force that we have, that we are applying in our hollow tube, is that value in the X direction. So why do we have this force here that goes down to 0? It should be around 4,000 all along the tube. The issue that we have here is that this force component 1 is not the force in the x direction in this case. How can we change this? How can we get the values in the actual x axis? Well, we can do this here if we come to explain, options, free body. What we are getting from the free body cat, from this force component 1, 2, and 3, are the forces that are normal and tangential to the plane. So actually, this Fx, this force x, is not force x. It's force in the axial direction of the tube. So, well, this is actually more useful for us. This is the force normal to the cross-section. If we still want to get it in global axis, we only have to change this coordinate system here. I will change it. Okay. And I'm going to rename this so that when we run the script again, we don't override it. So I will change this name, rename, and it's not force X, it's axial force. Okay. We have changed these options. So now I will select this viewport and run the script again. So file, run script, free body forces. All right. And now we have this force X. So let me come here to the right and plot both. Yeah, this makes a lot more sense. Now our force in the x direction is mostly constant. It should be perfectly constant, but because of the mesh that we have, it's pretty coarse, it's not perfectly constant. If we make the mesh finer, we will see a flat line here. To conclude, I would like to show you one more Python script that will run all the post-processing. You will not need to set before the viewcat, the x-plane, changing the coordinate system or not. It will do all for you, and we'll plot the curves in Abaqus as well, so you can export them later, or you can do whatever you wish. It's sort of for your inspiration. So we come here, file, run script, and the script has this name, post-force diagram. You will find it in the blog post at TecnoDigital School, and this is what this script gives us. It generates a new viewport and it creates a custom plot for us in which we have the axial force in this white color, the shear force in this red color. We can see that these forces are complementary in the end. We're rotating 90 degrees, so the value we have here around 4,000 is the same to the shear force diagram. And for the bending, we also have this dashed blue line that doesn't go to 0. Actually, it's maximum because it's this axis here on the left. Minus 0.18 times 10 to the 6, somewhere like that. Some quick comments about this script. We do the same at the beginning. We select the ODB from the viewport. Then we keep undeformed the view. In some cases, the deformation might be so large that the cuts don't make really a lot of sense, so better we can keep it undeformed. The next things that we do here is to select the cutting plane to enable the free body cut as well, enable the rotation, and in this line that we have down here, we select the coordinate system that we want to use. We will be using, in this case, the global coordinate system, because later on, we do the rotation ourselves. We rotate the forces in the x and y direction, and we project them in local coordinates of the beam. Very important here, if you don't want to have lots of xy data objects on each iteration, or maybe at the end, you can delete them. What I do here is I select the data objects that I have just created, and I delete them like this, as if you were deleting items in a dictionary. And I do this because I don't want to delete all of the XY data objects. In case we have some previous XY data before, like this, we will not delete it. And if we keep moving down, we have all the curves created here. And at the end, we plot these curves. We create an XY plot object like this. And then we add all the curves to this XY plot, to the chart in this XY plot. And at the end, we create a new viewport and we set it on the half right of the screen. So this is something that I've not used very much, and I wanted to try here. And that's all for today. Did you know about this XY data from free body cat function? Actually, this was a suggestion from a former student at the TecnoDigital School, and I searched for this, and I also got some help from him. So I appreciate it very much. Thank you, Abin, for this recommendation, and I'll see you in the next one. Bye.